Okay, welcome to the first in what should be a series of screencast videos for Math 1410 Elementary Linear Algebra at the University of Lethbridge for spring 2017. The first few videos will consist of review material from the first chapter of our textbook. This is material that is generally seen in high school, and if you are familiar with it, you can feel free to skip right ahead to chapter 2. Or skim through the textbook just to make sure that there's nothing there that you're not familiar with. Okay, so this first video will cover some material from section 1.1 of the textbook having to do with set notation. Now, as you go through this video and every other video in this series, a few things to keep in mind. One is that, of course, since it is a video and not a lecture, you can pause at any time. You can go back. If you get tired of my voice, you can turn down the volume. You can also speed it up or slow it down. If you want to get through it quickly, you can play it at double speed. It's a good idea to make notes of, any new terms that come up as you work through these things, and it's also a good idea to keep track of any concepts or examples or anything that you didn't understand, so that you can go and look up that same material in the textbook or ask about it in class, ask about it during office hours to make sure that you've understood it. Most things in this course are fairly straightforward once you've seen them a few times. So there are a lot of things that the very first time you see them, they're going to be confusing. They might seem a little bit strange. Some things you'll get right away. But maybe the first time you see it in this video, it doesn't make any sense to you. Then you go and you read about it in the textbook. It makes a little bit more sense. You see it again in class. It starts to click. You work on some problems, and eventually things will sink in. So as you watch through the videos, try not to be a passive viewer. Try to work with the videos. Do some problems as you go. Make notes as you go. And feel free to pause anytime you need to do any of these things. Okay, moving right along to the material, we begin with the definition of a set. Now, our definition is not a particularly rigorous one, but rigorous set theory is well beyond what we can do in a course like Math 1410. It's something that you won't see until very late. Well, actually, you probably won't even see it in your undergraduate degree here at U of L. We define a set to be a well-defined collection of objects. Now, this maybe doesn't seem like it helps at all because a collection is just an English synonym for set, so we haven't really gotten anywhere with this definition. The idea here is that you've got some group, some collection, some set, whatever synonym you want to use. You've got a bunch of things, and you've got some means of determining among the things you're looking at which ones belong to the group and which ones do not. So you've got some sort of selection criteria that you can use to decide between objects in the set. Most of the examples that we are going to see, examples of sets that we will look at, will be things like sets of numbers. There will be a number of sets of numbers. We'll look at some of them in the next video. Things like the natural numbers, which are usually denoted with a bold-faced capital N. Things like the rational numbers, which are usually denoted by a Q for quotient. The rational numbers are just the fractions. Real numbers, usually denoted by a capital R, and so on. So there are all sorts of different sets of numbers that we consider. In this course, we'll also be dealing with things like sets of vectors, sets of matrices, sets of points. So things like lines and planes, these are sets of points in some space, and so on. So there are a number of different types of sets where you can take any given object and you can decide whether or not it belongs to the set, right? So for something like the set of natural numbers, if somebody hands you well, if they hand you an object which is not a number, it's certainly disqualified right from the beginning, right? If somebody gives you a vector, that's obviously not a number. They give you a cat, or I don't know, a car, those are not going to be numbers, those are cats and cars. But somebody hands you a number, you can look at it and say, okay, natural numbers are the positive whole numbers. Okay, so is it a positive number? Yes. Is it a whole number? No, it was actually, 3/2 or something like this. And you say, okay, so that's not a natural number, it's a fraction. That belongs to the rational numbers. You have some way of deciding which numbers belong to your sets. Similarly, once we deal with vectors, matrices, things like this, in each case there's always some sort of decision process for deciding what belongs to your set. Okay, so how do you describe what is in your set? There are a number of different options. One is simply a verbal description. You write down a sentence that tells you what's in the set. So you might say something like the set of, let's say, positive even integers. That might be an option. There's one way of describing a set. We might just say something like the set of, say, 2x2 matrices with real entries. That's another way of describing a set verbally. The roster method is the method for describing a set where you simply list the things that belong to the set. So maybe this set of positive even integers, let's give that thing a name. Let's call it A. So then we might say, well, what is this set A? A is the set containing the numbers 2, 4, 6, 8, and so on. And we just simply write out the elements in this set. You'll notice the use of the equals sign here. In the context of set theory, when you say that two sets are equal, you just mean that they have exactly the same elements. So when I write out a sentence like this, A is equal to the set containing 2, 4, 6, 8, and so on, I'm telling you that the numbers 2, 4, 6, and 8, and the ones following that pattern are exactly the elements that belong to my set A. The set of 2x2 matrices with real entries, that's something which doesn't really lend itself very well to a roster method description. If we call that thing, let's call this set maybe B. But I can describe that set using what's called the set builder notation. So I could say, well, B is the set of all things that look like A, B, C, D. So a 2x2 matrix is some sort of object like this, which has some numbers arranged into 2 rows and 2 columns, and I want to specify that these numbers A, B, C, and D within that matrix are real numbers. So then I say, okay, A, B, C, and D are real numbers. So that's an example of using the set builder notation. So you use some dummy variables, in this case A, B, C, and D, to describe the objects that are in your set. If we were dealing with the set of even integers, we might say something like this. We might say, well, A is the set of all things that look like 2 times K, where K is a positive integer. So 1, 2, 3, 4. And so on, like that. Or maybe instead of writing out a list like this, so here we're kind of combining the roster method and the set builder method, we might say something like K is a natural number, and then we're using a verbal description within the set builder notation. So all of these are perfectly valid ways of describing a set. Now if I want to tell you that something belongs to a set, a particular object belongs to a set, I use this membership notation, this guy right here. So this funny looking E, this is the element symbol. And it's used to indicate that a given object is an element of a set or a member of a set. There's a lot of English synonyms here. There are a number of ways that you can read this sentence. I mean, this is kind of a funny looking sentence. It's a symbolic sentence, but it is a sentence, right? The verb, if you like, is contained within this element symbol here. So when I write something like x is an element of A, that means that x belongs to A. Or I could say x is a member of A. Or x is an element of A, x is in A. There are lots of equivalent English sentences that mean the same thing as this membership notation. So for example, I could say that the number 46 is an element of the set of all positive even integers, right? 46 is in there because it is a positive even integer. 47, being odd, is not, and the way we say that a number does not belong to a set, it's the same way that you might say that one number is not equal to another number. You just put a line through that symbol to indicate the negation. Okay. The other bit of notation that you're going to run into in this course is subset notation. So the sort of visual representation of subsets, if you kind of think of your set as some sort of blob, right? So there are some elements, right? And some of them belong to your set, and there might be some other ones which do not belong to your set. And then within this larger set B, you have a smaller set, let's see, A, and so every one of those points, so I'm using points to represent elements of my set, so one of these guys here, maybe this guy is X. X is an element of A. Everything that is within that red circle indicating the set A is also within the blue circle indicating the set B, and so I would say that A is a subset of B because everything that belongs to A also belongs to B. Whereas if I had, let's draw another set in here. Maybe I have a set C, something like this. So in this situation here, using this notation, I would say that A is a subset of B. Okay, so this subset notation, this kind of funny looking C with the bar underneath, is used to indicate that every object which is an element of A is also an element of B, and we can see that that holds here. However, for the set C, we would say that C is not a subset of B because although this object here is common to both sets, so that is an object which is an element of C and happens to also be an element of B, we have the more important guy is this guy out here, right? So this guy is an object which belongs to C, but it doesn't belong to B. So this set C cannot be a subset of the set B. Okay. One final thing to add, the little bar underneath, if you're wondering about that. Note that it's true for any set that any set is a subset of itself, right? Because if X belongs to A, then X belongs to A. This is basically a tautology. So you should think of the less than or equal to notation for numbers, right? If you're using less than or equal, that's something which holds if X is, say you write X is less than or equal to Y, that holds if X is smaller than Y, but also if X is equal. Similarly with sets, if I say that A is a subset of B, well, it might mean that A is a smaller set, or it might mean that A is in fact equal to B. The important thing is the defining condition, this guy right here, that everything which happens to be an element of A must also be an element of B. Alright, so we will stop here for the first video. and we will continue in the next one with the real numbers.